So if you back up to amphibians, amphibians, one of their problems is that they are tied to what? Water. They must reproduce in water. They have to lay their eggs in water. They have to hang out near water. One of the reasons is their skin is kind of like porous. In fact, that's why frogs and like salamanders, they're one of the like warning signs of chemicals in the water, because like they'll start showing up with like 3 heads and stuff if there's a bunch of like weird chemicals in the water. So they have the ability to colonize land, but only like a couple miles in on land, whereas reptiles and birds had the ability to colonize like pretty much anywhere on land. And one of the adaptations, so there's a lot of like so one of the adaptations for land is their egg. They have what's called an amniotic egg. Did I spell that right? Egg. And an amniotic egg means it is self-contained. It has what's called the amnion inside it. But unlike a salamander egg or a frog egg, right, that has to hang out in the water, frog eggs are porous. Water can get in, waste can get out, oxygen can get in, carbon dioxide can get out. So the little like tadpole egg, right, as it's developing, it actually can breathe through the egg's like surface and skin. Whereas amniotic eggs are like fully self-contained. Usually what happens is there's a little like developing embryo, right? And that's attached to a yolk. And then there's often other fluid like the amnion or amniotic sac, which you all were in at one point, which is why humans are also considered amniotes. But yeah, there's an amniotic sac. Sometimes there's other sacs too for like, I don't know, like a patch of air. You've all seen like the little gap of air chamber in an egg. When you have a hard-boiled egg, there's always a little section that's at one end usually. It's empty. But the point is that the developing chick, right, like bird chick or reptile chick, reptiles, do they have chicks? Babies. Can develop inside this egg. Sometimes it even actually, most of the time, it even has a shell. There's a waterproof shell. So a waterproof shell, which isn't about preventing water from getting in, it's about preventing water from getting out. Yeah, so that's why you can have organisms live in the desert. Like turtles and reptiles and snakes and things like that, is because they have these amniotic eggs. Let's talk about reptile skin. And bird skin for that matter. What's it like?
Rough.
It's rough, yes. Wait, how do you spell rough?
R-O-U-G-H.
Didn't look right for some reason. It's scaly. It's dry, right? They don't need to have water on their skin. They're covered in these scales. And again, it's if you don't have water on the surface of your body, you can't lose water to evaporation. Okay, next up. Both reptiles and birds have lungs. We'll get to bird lungs in a second. Reptile lungs are pretty basic, like mammals. But reptiles, unlike fish, actually, let's back up for a second. Let's draw a fish heart. Let's use red. So the point is, reptiles and birds have lungs. That's it. That's all we're going to put there. But let's talk about a fish heart. Let's talk about hearts. So in a fish heart, blood is coming from the body. It fills up a sac called an atrium. It moves from the atrium into, this is just like a filling chamber as it fills up, fills up, fills up. And then it goes into this second chamber that's muscular. And it does a big old pump, squish. There's usually a valve between them. And then it squishes the blood up forward toward its gills. And then after it leaves the gills, it goes to the rest of the body, and then it goes back. So we have the atrium and the ventricle. Fish have a two-chambered heart. One atrium, one ventricle. Abby, put the phone away. Take some notes, please. Amphibians and reptiles have a three-chambered heart. So theirs looks a little bit more like this. They have blood coming in from their from the body. And some blood coming in from the lungs, and they fill up these atria. And then there's a valve, and then there's this big old ventricle at the bottom. Something like that. Atrium there. They have a left and a right atrium, and then one large ventricle. So amphibians and reptiles have a three-chambered heart. How many chambers are in your heart? 4. Yep. Mammals have a 4-chambered heart. Birds. We'll cover this again when we do human anatomy notes. But you have 2 atrium. And then the ventricle here is similar to the reptile one, but then it's divided in half, actually. So there's a big old divider down the middle. We'll draw the tubes coming out, but there we go. So mammals and birds have a 4-chambered heart. You have 2 ventricles, a left and a right ventricle, and a left and right atrium. And the cool thing about the 3-chambered heart is you can start separating out the blood that's going from the lungs and from the body. The 4-chambered heart is where it's on 2 complete circuits. So the blood goes to the lungs, and then it goes back to the heart, and then it gets pumped out to the body. And there's no mixing. So here in the reptile and the amphibians, the oxygenated blood mixes with the oxygenated blood, and then it spreads out. It's just a little bit less efficient. But it is really handy if you have periods of low oxygen, like as if you were growing in an egg. In fact, you were all born with a 3-chambered heart. And then as you develop, there's basically a hole between your 2 ventricles. As you grow older, that hole should close up within the first week of birth. That's one of the things they check for when you have a little baby, is they'll, you take them in for their week-old checkup, and they'll listen to their heart and be like, oh, is there a hole in the heart? Some of you guys may have had a hole in your heart and had surgery. Okay, a couple other reptile adaptations while we're on reptiles. They have a cloaca or a cloaca. You guys heard of this? Organ, section, body part, what is it?
The one waste hole.
The everything hole. Boop, boop. Generally, on the back side of like a lizard or a bird or something like that, you're going to have this hole that's the intestines lead to, the bladder leads to, and then the testes or ovaries lead to as well. So it's this combined urogenital opening is the official term. And again, it helps with preventing water loss because you have fewer openings out into the hot, dry earth, including things like the water can get reabsorbed before it fully leaves. And in fact, instead of using ammonia like a fish does for nitrogen waste, you remember what birds use? They don't use, well, okay, how do you get rid of nitrogen waste? P, but what's in P? What's the part, the actual like nitrogen molecule in P? No, ammonia is more in fish and like babies and stuff. There is a little bit of ammonia in humans, but it's relatively small. There's another word that starts with a U. Urine? Close. It's related to urine. It's a molecule called urea, right? That's sorry, I missed it. Yeah, urea is in urine. In birds and reptiles, they use uric acid. Which is basically a way to get rid of nitrogen, but it doesn't require much water. You can just think of it like that. Whoa, H2O. Okay, finally I'm going to draw a little phylogeny. I know you guys are a little bit sick of these, but that's okay. You'll survive. We're going to have branching off over here. We're going to have mammals. And then we're going to have some reptiles. Like, oh, I should just draw them. I drew a turtle. Right? Great. Cool. And then over on this branch and this branch, we're going to have a little snake. And we'll have like a lizard. Close enough. Anyway, turtles, snakes, lizards. I guess we could throw crocodiles in here too. That's my crocodile. Close enough. Okay, and then finally, past the crocodiles, we have two groups, like that. They're gonna branch off. Here's where it gets a little weird, and I don't know why they've classified it this way, but probably because when you look down in the details, it makes more sense. The weird thing is, reptiles don't make a good monophyletic group. They're a paraphyletic group because they have all of these branches, but crocodiles, for example, are going to be more closely related to these guys over here than they will to, you know, lizards and snakes, right? So therefore, they're not monophyletic. In fact, this branch here is the dinosaur branch. And so down these two branches, you have things like T-Rex, that's an ugly T-Rex, but you get the point. And then the other major group on the dinosaur branch are the what? The birds. Just birds in general. These dinosaurs are what you call the non-avian dinosaurs. And this is aves, or birds. So the pedantic part of me is like, oh, every time somebody says like, oh, all the dinosaurs are extinct, I'll be like, actually, like the dinosaurs are still around. We got lots of them. The birds are considered part of the dinosaur like clade or group. So just keep that in mind, that birds are very dinosaur-like. If you've ever, like, I don't know, raised turkeys or something like that, they act like little velociraptors sometimes. All right, just a few bird-specific things. Talk birds. What makes birds different than reptiles? Will, head up, come on. Take some notes. It's not hard. What? Yeah, birds are warm-blooded. So what's the correct term for being warm-blooded? You guys remember? Birds are endotherms. Which means they maintain like a steady body temperature. And it's usually a higher body temperature than the environment. But unlike lizards where they have to like sit there and sun themselves to warm up, birds use their metabolism, the food that they're eating, to keep them warm. What else do birds have? What's the obvious one? Wings. Yeah, they have wings, or let's start with feathers. They have a few adaptations for flight. Feathers provide a few things. One is flight. But what else do feathers provide? Yep, warmth, insulation. And you probably won't notice it unless you like watch a video of a fox trying to bite a grouse or something like that. But what else do feathers provide? Protection, yep. And feathers, by the way, are modified scales. Just like fish scales, they're just modified fish scales that are super long. What other adaptations do they have for flight? They have wings. So their upper pair of appendages have been modified for flight, which gives them a huge advantage, being able to fly around all over the place. What's true about their bones? Yep. Draw a very good bone here. Anyway, inside they have lots of, it's not completely hollow, like totally empty, but they have lots of like spongy bone tissue with lots of air inside. So they're light, or a higher strength to weight ratio in their bones than a lot of animals. We talked about their hearts already. Four-chambered heart, which incidentally evolved independently of like mammals, and our four-chambered heart. But there's something special about their lungs. Does anyone know? They have lungs that are more efficient than a human's lung. So a human lung, or a mammal, looks something like this. right? You breathe in, suck a bunch of air into your lungs, and then what happens to that air? It exchanges its gases with your blood, right? In the little like tiny air chambers. So what gases are being exchanged?
Oxygen, carbon dioxide.
Yeah, oxygen and carbon dioxide. Oxygen is going into the blood, carbon dioxide is going into your lungs. But the problem is, how efficient, what's the maximum efficiency that can be? But even then, let's say you get perfect diffusion, right? Can you get all of the oxygen in your lungs to diffuse in your blood? Why not? But it's not the level of oxygen in the air. It's the fact that the diffusion only goes against the concentration gradient, right? You can't have all of the whatever diffuse into all of whatever space. You can only have half of it, and then at that point, the concentration is even in both, right? So you can only have half of the oxygen in your lungs get diffused into your blood, and only half of the carbon dioxide diffused into the air in your lungs. So they're not particularly efficient. Birds, however, that's a mammal. Birds have a super efficient system. So they have air coming in here, and then what it does is it fills up a series of these like sacs. So the air comes down, it fills up these sacs, and at the same time, as it's filling up these sacs, it's filling up a second set of sacs up here. So something like this. I don't know if I drew it perfectly well. So as it's filling up, this air is filling up from the air outside. This air is filling up from these sacs here. So as they breathe in, the air is filling up these sacs, and it's moving the air this way to fill up these sacs. And then when they exhale, this air moves across, this air leaves, and then they inhale. So the air is constantly going in a circular motion. It goes in and out at the mouth, but down in the air chamber, it's going in this circular pattern. And that's really valuable because then they have like this section of one-way airflow. And since there's one-way airflow, they can do a countercurrent exchange. Their blood can go in this direction. The air is going in this direction. And they can actually exchange like 95% of the oxygen in their lungs with the oxygen in the air. So it can like about 95% efficient. Whereas our lungs are about 50% efficient. Actually, less than that, but sometimes more. So you imagine getting twice as much oxygen out of each breath. That's super, super important, especially when you need to fly places. Who do you need?
Just get into the student and have them head down to counseling at like 8:30.
Okay.
Yeah.
Sounds good.
Yep.
All right, we're gonna call it there for notes, actually. Here's the plan for the rest of the class period. It's your final chance to work on what? Yeah, your lab write-up is due next time we meet. How does it need to be turned in? Printed out at the beginning of class, yeah. So if you need to run to the library to print it out today because you finished writing it, great, just get a pass. If you want to share it with me and I can print it out here, that'll work too. But let's try and knock it out if we can today. That way you don't have to finish it up as homework. Okay, very quick.
Oh my God, I'm so excited.